Hey everybody, we are back. Welcome to session lesson 1.1 of the 2024 STEMNetX coding workshop. Your host Mike McCracken back again. So the last lesson's video was very long. Goodness was it long. Partly that was because I talk a lot, and partly, I'm doing it again right now, partly that was because we had a lot of ground to cover just in terms of basics and getting set up. So this video should be shorter. I want to just remind you how we get the notebook files for the workshop. So I'm back here on my GitHub page, STEMNetX Coding Camp, Asynchronous Workshop. I'm going to go to lesson 1.1 and then click the download button right here, download raw file. That will download, and then what I'm going to do is I'm going to go back to my Jupyter Notebook tab, click upload, and then find that file that I just downloaded in my file browser. There it is, async STEMNetX _1.1 control structures.ipynb. And I'm going to open that. Yeah, we'll overwrite. And then I can just open up that notebook file. Okay, so we're in. Lesson 1.1 is all about this idea that we call control structures, which generally just means what are the structures that we use to control how our code, our programs, our software runs. Before we dive into that, I want to do two things that are going to kind of be a standard feature of each of these lessons after 1.0, which is first we'll do a recap, or at least first there is a recap section. This is all of the ground that we covered in the first lesson. There's a lot of stuff here. We're going to build on this today. We will refresh some of those concepts today or in this lesson. But actually, the point of this section is that we've already done quite a bit, or we've introduced quite a few ideas or topics, even if it maybe feels like you've just barely gotten your feet wet. Second, I will leave this motivation section for you to click on later. There's this cool video on YouTube of something called the Mandelbrot set hard zoom. The Mandelbrot set is a mathematical object that exists in the complex plane. It's produced, or it's investigated, or it exists. It's defined by this iterative process of doing this computation z squared plus c over and over and over again. So you start with some number z, you put it into this function z squared plus c, where c is a complex number. If you're not familiar with complex numbers, that's totally fine. And then this process happens over and over and over again. And you basically do some coloring of the 2D plane or the complex plane based on how that function goes or how that mapping goes. You can click on the hard zoom video. It's really wild. It's really interesting. The takeaway is this is a really complicated area of mathematics to investigate, the fractals and these sets in the complex plane. You basically, or at least after today, will have most of the fundamental or foundational skills for working on a problem like this. You might need to bone up or learn something about complex numbers. But the basic programming structures are things that you'll be familiar with. All right, let's dive into it. Control structures, what we're talking about today. Control structures are structures that control the way our code will run. Broadly, control structures fall into two categories. The first is what we've already talked about just a little bit, is what we call loops. Looping is a way of making a computer do repetitive tasks over and over and over again. Second is what we call conditionals, which are ways to make the computer's behavior depend on some type of parameters in our calculation. So we're doing a calculation based on the value of a quantity that comes up in that calculation. The program will either do this or do that. So it's going to choose some behavior based on information that exists within the program. I'm going to move my webcam over just a little bit because I'm sliding off screen. All right, great. So let's go back to loops. We use a loop when we need to do something over and over and over again. So here's like a really basic idea. I have a little loop here. It's a for loop. We talked about for loops very quickly in the previous lesson. And here's a really dumb use of a for loop. If I run this code, this cell, what it's going to do is it's going to print out. We use a loop when we need to perform some task over. And then for I in range 10, which means do something 10 times and set the value of I in each pass through this loop to be 0, then 1, then 2, then 3. It's going to print and over each time through the loop. It's basically not even going to use that I because it doesn't show up in the code inside of the loop. And then once we exit the loop, it's going to print again. So check out the behavior that this cell gives. We use a loop when we need to perform some task over and over and over and over and over and over and over again. So if I really wanted to convince you of how we use a loop, I would write out, we do this over and over and over again. That's a repetitive task, so I actually just used a loop to do that repetitive task for me. That's so meta. So in the previous lesson, we talked a lot about why it is that we use computers to do mindless work like this. In this lesson, we're going to talk about how we do that and actually what are some of the use cases. There are several different ways to think about categorizing or characterizing the ways that we implement loops. First, I want to start off with this distinction between what we call iteration and recursion. So these are both repetitive tasks or examples of repetitive tasks, but they have a very important difference. An iterative task or an iteration application is some type of loop structure, some type of repetitive structure, where the calculation in any one step of the loop doesn't depend on any of the previous calculations in the loop or any of the previous iterations through the loop. This is what we call iteration. So an example of an iterative process would be exactly the example that I showed you previously. We did this over and over and over again. Let me just add something here. So I'll put in here, I'll add to my print statement. We'll print and over, and then the value of I in that step of the loop. And here we wind up with, probably exactly what we would have guessed. The point I want to make is that this is an iterative process because the value at some later step in the loop basically has nothing to do with the outcome of a previous step in the loop. All I'm doing is just printing out a number. It's not like when I is equal to 5, it's not like what's going to happen the next time through the loop really depends on what happened in the previous time through the loop. So that's what we call an iterative process. Other examples would be like, let's say you want to sum up a bunch of numbers from 0 to, 2000 or 2022, something like that. You could basically begin that sum at any number between 0 and 2022. You could begin at 100 for no reason. It's kind of less arbitrary to start at 0 and end at 2022. You could go backwards. The outcome of that iterative process doesn't really depend on where we start. Recursion, on the other hand, is the opposite. So in a recursive process, the calculations that are done in some step of the loop depend on the outcome of the calculations in a previous or some previous steps in the loop. So this is, as you can probably guess, usually a much more complicated application. We have to be much more careful about how we would code up an iterative process. A good example would be something like, let's say you have invested some amount of money in the stock market, or you've invested it in some type of fund, which, spits off a certain amount of interest. The amount of money that you have in that investment in 1 year depends on how much money was in it in the previous year and how much interest it accrued in the previous year. So we can't just, if I tell you, hey, I'm going to invest $100 in this stock, you can't just ask me, okay, how much will you have 10 years from now? The answer is, I don't know, we got to wait and see. Each year I'm hopefully going to get a certain amount of positive return on that stock, but we don't know until that iterative process, until we actually chug through the process of the stock going up and down. So this is just one way of classifying the types of applications that we use loops for between iteration and recursion. We're not going to talk about this too much more, although we will do examples of both of these. They'll just kind of come up naturally in the types of problems that we investigate. The more useful distinction that we will make in coding up loops or iterative or recursive processes has to do with whether the loop is a definite loop or an indefinite loop. So this is, again, a loop is a type of thing that you would do in the service of doing some type of calculation. A definite loop is a loop structure where you definitely know how many times that loop is going to have to execute before you even run the program. So if, for example, if I wanted to sum up the integers between 0 and 2000, I would know that that loop has to happen 2,000 times. I know ahead of time it's going to happen 2,000 times. For each number between 0 and 2,000, let's say we ignore 2,000, so we only have the numbers 0 to 1,999, so 2,000 of those numbers. I know that I only have to include 2,000 of those numbers. So that's a definite loop because we know ahead of time exactly how many times that loop is going to run. Here's an example of a definite loop that we've encoded with a for loop structure. So for I in range 10, print I. I mentioned in the previous lesson that this thing range 10 is basically the equivalent, not quite, but this is fine for our purposes. It's basically the equivalent of building a list of numbers that goes from 0 up to and excluding the number that we put in parentheses here. So range 10 is going to create a list of numbers. It starts at 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then stops right before it gets to 10. I know, even in looking at this code, because of the way it's written, for I in range 10, this loop is going to happen for each value in this object range 10. There are 10 numbers in there, 0 all the way up to 9. So I know that this thing is going to happen 10 times. Now, this is a dumb example, but there are many types of calculations in the quantitative sciences that can be encoded as a definite loop. So let's talk about the syntax of this thing. And again, we did this very quickly in the previous lesson. The syntax of this for loop, this for structure, is I start with the keyword for. That's a special type of word in Python that tells Python, hey, get ready. I'm going to be telling you how to do a for loop here. Then I have I. I is going to serve like a variable whose value is going to change each time through the loop. In is another keyword. You see it's kind of bolded and in green here to tell us that it's a keyword. It's basically, this structure says you're going to successively set I equal to each of the values in this object range 10. And again, that object range 10 is just a list of integers from 0 up to right before we get to 10. So that's the structure. The colon is a very important thing here. The colon basically is telling Python, okay, listen, I have structured this for statement. I've told you everything you need to know about how to iterate over, change the value of I every time through this loop. I'm going to put colon here, and then right after that colon, I'm going to have a set of instructions to do every time through this loop. It's very similar to the way that we use a colon in written English. If you wanted to list a whole bunch of things, you would say, here are the things that I had for lunch. Colon, 2 hard pretzels, comma, 2 slices of cheese, comma, some celery, comma, some bluey fruit snacks. Okay, I'm not embarrassed to admit it. Very similar here. We have the colon. We're saying for I in range 10, colon, and then we're going to have a list of the things to do every time through the loop. Now, in this case, we only have one thing to do. It's just printing out that value. All of those things that we want to happen each time through the loop are going to be indented one level. So the way that we do this, the way that we literally type this into a cell, is I would hit enter, and then it'll kind of auto tab complete. But if I started typing here, and I wanted this stuff to be part of the loop, I would hit tab, and it automatically indents that to the level that Python wants to see it for it to be included as part of the loop. Okay, okay, so that covers all that stuff. All right, so let's do a warm-up problem. The syntax here is I'm going to say basic, it's straightforward, but it's going to take a while. It's going to take a few examples for us really to get the hang of this. So here's a warm-up problem. Add up the even numbers between 0 and 2022. All right, so the first thing that I have to do is I'm going to create a variable called sum, which is just going to keep track of the sum, all these things that I'm adding up. You can think of sum as almost like a jar, and I'm just going to be dumping more and more even numbers into it, and then at the end of the problem we'll see how many things are in the jar, or how much number is in the jar. Then I'll do for I, and it doesn't, I can call it whatever I want, for B in range 2022, let's interpret it that way. What I'm going to do is I'm going to set sum equal to the previous value of sum plus B. So every time through the loop, I'm going to set a new value for B, and I'm going to add that value of B onto my sum right here, and then I'm going to store that resulting value in the variable sum. Okay, and then at the end of the loop, what we'll do is print out sum. Now, you may notice that this is not a solution to the problem. So what I've done incorrectly here is that this code doesn't sum up just the even numbers, it sums up both the even and the odd numbers. So I have to be a little bit more clever about how to do this. One way that you might think about doing this is to say, okay, well, for each value of B in this loop, we should only add B onto the sum if B is an even number. If you're thinking that right now, awesome. You have a very programmy type brain, a very computer sciencey type brain. The only problem is we don't know how to do conditionals yet. That's later on in this notebook. So for right now, we need some other sophisticated way to do this. I think what I'm going to do is the following. Whoops, that's not right. 1011. And then for each time through the loop, I'm not going to add b onto that sum. I'm going to add 2 times b onto that sum. So what this is going to do is when b is equal to 0, it will add 2 times 0 onto the sum. When b is equal to 1, the next iteration through the loop, this will add 2 times 1, or 2, onto sum. The next iteration through the loop, b will be equal to 2. This is going to add 2 times 2 onto the sum. So I'm going to loop over I'm going to loop over all of the integers, even and odd, but I'm going to multiply each one of those integers by 2, which of course will give me only the even numbers. In order to do that correctly, I have to reduce the total number of integers that I'm including here. If I really wanted to check this, I could do something like this. I'll print out 2 times b, the thing that we're adding on, just to make sure we are getting only the even numbers. And you see that the print statements here that I get are only the even numbers. Let's see if it goes up as high as we want it to go. Yeah, it goes up to 2020, which would be the last even number less than 2022. And of course, here's the sum down here after we exit the loop. So I'll get rid of this just so we have nicer output there. Look, looks great. So that's an example of a definite loop. So this type of problem, this seems like a really basic problem, and it is, but it's not very different from a lot of the less basic problems that we'll solve later. That's an example of a definite loop. The flip side of that coin is what we call an indefinite loop. So an indefinite loop is a loop in which we don't know how many times this thing has to execute before we actually run it. That is much more akin to a recursive process possibly, or a process where we have to decide on what we want the problem or the program to do based on the state inside of the loop or the state of a variable or something like that. So an indefinite loop is a loop for which we can't hard code the number of iterations. An indefinite loop is kind of, you could code it using a for loop, but typically we don't do that. It's a little bit clunky. There is a different loop structure, or a different loop keyword for doing that, or a different control structure, and it's what we call the while loop. A while loop runs, it continues executing, as long as the condition after the while keyword is still true. So there are 2 new things we have to introduce here. One of them is while. It's not too difficult to understand. It's just like a for loop, only the stuff inside of the loop is going to execute while something is true. The second thing we need to introduce is this idea of a conditional, or sorry, this idea of one of these comparative statements. So check out what this program is doing. I'm establishing 2 variables, loop max, which is equal to 1000, and loop count, which is equal to 0. This loop is going to execute as long as loop count is less than or equal to loop max. Every step through the loop, I'm going to increment loop count by 1. So basically what loop count is doing is it's counting up the number of times I've gone through this loop. Every time I go through the loop, I add 1 onto loop count because I've gone through the loop one more time. And then every time we go through the loop, this while is going to check whether loop count is less than or equal to loop max. And I'm actually going to turn this down. We don't need to see that I like bikes 1,000 times. We'll just do it 10 times like this. So there's a lot of stuff here that's similar to a for loop. There's some stuff that's different. It's a different type of thing. This is, in this case, we can tell ahead of time how many times this loop is going to run, but it's only because the math here is very straightforward. This thing's going to run, we're just going to add 1 onto loop count each time through the loop, and then stop when loop count is greater than 10. This is a very, very simple example to demonstrate the syntax of a while loop. So all of these comparisons, you can see more of them in here. We have less than, greater than, less than or equal to, greater than or equal to. The double equals sign checks whether 2 values are actually equal to one another. Remember, what a single equals sign does is it assigns a value to a variable. So if I do just like we had above, loop count equals 0, that is assigning the value 0 to that variable. If I want to check whether 2 variables or 2 quantities are equal, I use a double equal sign. It's a different type of thing. I'm not setting the value, I'm comparing 2 values. Exclamation point equals, we usually that's the not equals operator. It checks whether two things are not equal to one another. It returns true if those two things are not equal to one another, and false if it returns true if those two values are not equal to one another, and it returns false if those two values are equal to one another. So it's a little bit confusing, right? It seems to work backwards. You can also use this not keyword if you just want to negate, something that some other comparison that you've written here. So we can actually execute this code cell and see the outcomes of these comparisons. Is 2 less than 1? False. 2 greater than 1? True. 2 equal to 1? False. 2 not equal to 1? True. Okay, this one's tricky. 2 greater than 1, not. So it's like opposite day. Is it not true that 2 is greater than 1? Well, 2 is greater than 1, so this is true. But then if I take the opposite of that, I get false. So if I negate that, I get false. It's kind of logically tricky. I don't know why you would code up something like this, but just for example purposes. So here's the type of thing that we could do with one of these indefinite while loops. Here's a problem that I may have alluded to before when I was talking about investments. So what if I deposit $1,000 in a bank at a 2.1 interest rate per year? How many years will it take before I have $1 million in the bank? Now note, this is not me asking how many dollars will I have in the bank 20 years from now. It's kind of a different question. It's saying my goal is to have $1 million. It's a fine goal if it's your goal. I want to know how long will I have to wait until I do that. Well, here's a way that we could code that up. Now, what's going to happen inside this loop is I'm basically adding interest to my investment every year. I'm changing the value that I have deposited by taking the previous deposit value and multiplying it by 1 plus the interest rate, so 0.021. So if I want to know how much money I have in the bank, how big my deposit is in year 6, I first need to know how much money I had in year 5. This is an example of a recursive process. The calculation in year 6 depends on the outcome of the calculation from year 5, which depends on the outcome of year 4, which depends on year 3, which depends on year 2. So I can't answer this question right out of the gates. There may be some mathematical tricks that I could do. If you know a way to do this, just post it in the comments. I don't know, whatever people do on YouTube. All right, so when I run this, you already see the result there. I should have deleted that, dang it. All right, so this while loop is going to run as long as it's going to run while my deposit is less than 1 million. Once this comparison is no longer true, the loop is going to exit and the code will print out the year. So when I run this thing, it runs, almost instantaneously. It's so dang fast. And it turns out that I would need 333 years in order to have at least $1 million in this deposit. If your goal is to get $1 million, this is probably not a good strategy. So we now know that. We've answered a question. This is great. That's like data science right there. Okay, so there is a way to check this with the standard formula. Here's what it is. I would do 1.021 to the 333rd power and just multiply that by my initial deposit. And we find that we have over $1 million. So once we already know the answer, the number of years, I can plug this into this formula and just check it. There you go. That's an example. All right, I will let you read this iteration and recursion revisited. I've touched on iteration and recursion a couple times, but really we've been thinking more in terms of definite and indefinite loops. That's great. Two different ways. They're kind of two different perspectives to investigate what we're doing with these loop structures. All right, let's move on to conditionals. The idea of a conditional is, I think, fairly straightforward. It's this. We have some code, it's running. We want the behavior of that code. We want what that code does to depend on the result of some type of calculation or the value of some quantity that's been calculated in the code. The way that we do that is with an if statement. You may recall that I kind of mentioned this, like we could code this up. Earlier we were doing an example and I said, what if we only added the number onto the sum if that number were even? We didn't know how to do that back then, but we're about to know how to do that. The if word in Python is a keyword. So you can see how this thing does. It works in some ways kind of like a while loop. So a while loop had while and then some type of condition that gets checked. An if statement has if and then some type of condition that gets checked. If that condition is true, then the stuff in that while statement is going to happen. If that condition is not met, if that condition is false, then the stuff inside the if statement is going to be ignored and the program just kind of skips on to the next lines. So here's a very basic example. It's similar to what we did before. For I in range 10, well, that's just going to loop over the numbers 0 through 9 and set the value of each one of those successive numbers, or set I to be equal to the value of each one of those successive numbers. Then what's going to happen? Well, for each step through the loop, each iteration through the loop, if I %2 is equal to 0, remember that percent is modular division. So this is going to say divide I by 2 and check whether the remainder of that thing is equal to 0. If it is equal to 0, print the number and is even. Because if I %2 is equal to 0, if I divide I by 2 and have no remainder, that number is in fact even. When we run this thing, that's exactly what we get. So notice that for I equals 1, I equals 3, I equals 5, nothing is happening here because if the condition in the if statement is not met, it's going to be false. So the loop just proceeds on and then starts over. We have nothing for the loop to do if I is odd. Okay, if we wanted to build in some more sophistication here, I'm going to, let's leave that there. If we wanted to build in some more sophistication, if we wanted multiple clauses, we could do that with multiple if statements, or we could control that behavior with what we call if, else structure. So check out what happens here. We're basically going to have 3 conditions, and they're going to be evaluated depending on what happens with the previous condition. So if I divided by 2 remainder is equal to 0, we print I as even. ELIF is Pythonic for else if. This is basically just a way of saying, okay, if this first thing is true, then do this. Else, meaning if that first thing wasn't true, if this thing is true, then do this second set of instructions here. Else, meaning if none of the previous conditionals evaluated true, just do this last thing. So let's check out what this does when we run it. Okay, when I is equal to 0, we're first going to check I divided by 2, remainder is equal to 0. That is true, so our code is going to print 0 is even. Boom, that's what we got there. What about I equals 1? So this is the next step through the loop here. Well, if I is equal to 1, this first condition will not be true. So this print I is even will not happen. This second condition will not be true. This second condition basically checks whether the number is divisible by 3. 1 is not divisible by 3. So this stuff is not going to happen. What we're left with is this else statement. Else just means like, well, if none of the previous things was true, then just do this last thing. And we can see what we get printed out is that 1 is neither even nor divisible by 3. This is a goofy thing to check. You know that 1 is neither even nor divisible by 3. But this is, again, just an example of a control structure that we can make great use of. All right, let's check out this snippet right here. This is basically just the previous code cell on steroids. So what this is going to do is it's going to count up the number of integers between 1 and 100 that are divisible by 7 and the number that are divisible by 11. So I have 2 variable names here. N div by 7 basically just means the number that are divisible by 7, and then same for n div by 11. I have a for loop because we're going to do this for each integer between 1 and 100. Notice there's a little bit of a different syntax for the range statement here. I can supply a lower bound as well as an upper bound. And, let's see what we're doing here. Yeah, so we're printing out, check this out. So we're printing out, we're checking whether the cube of this number is divisible by 7. Or whether the cube of this number is divisible by 11. So that's kind of interesting. So, well, I think it's kind of interesting because I came up with it. When we run this thing, so the first iteration through the loop, I is going to be equal to 1. It will cube 1 and check whether it's divisible by 7. Nope. It will cube 1 and check whether it's divisible by 11. Nope. So none of this other stuff inside of that loop is going to happen. the loop is going to start over and set I equal to 2. And it's just going to keep churning through those. Once we get to the first number whose cube is divisible by 7, which I don't know, that might be 7. It's going to check this. It's going to print out the number. It's going to print out the cube of that number, and it's going to increment this counter by 1. It will say, hey, I found a number whose cube is divisible by 7. Increment the value of the number that I've found that are divisible by 7. So if we run this thing, check it out. The first number that we have that's divisible by, whose cube is divisible by 7 is 7. I was right. You cube 7, you get 343. That's by definition divisible by 7. The first number whose cube is divisible by 11 is 11. 11 cubed is 1331. So there we go. And you can see the other values in here. At the end of this program, it turns out we found 14 cubes divisible by 7, and we found 8 cubes divisible by 11. Again, not hard-hitting, mathematical revelation here, but an example of a structure that we will use later on. So these control statements are very, very useful. Okay, lastly, I want to talk about a connection to something that you probably encountered before. If you've taken a calculus class, you've talked about integration. When you take Calc 1 or Calc 2 or sometimes Calc 3, you learn a lot of really cool tools or formulas for doing integration. So you have a lot of rules. There's like the power rule and the exponential rule and a logarithm and some rules for trig functions and things like that. Very often in the quantitative sciences, we need to integrate really nasty functions for which there are no convenient integration rules. So here's an example of not what I'm talking about. This is a polynomial. F of x is equal to negative x cubed plus 4x squared. If you've taken Calc 1, this is like bread and butter integration. You use the power rule, you could do an indefinite integral, you could do a definite integral, great. I'm just going to use this function to demonstrate what we want to do here. So I'll define this thing as a function using the technique that we did yesterday. This block of code is basically just going to plot out, make a graph. You can ignore that block of code. When you're running this notebook, run that block of code so you can see this thing. If you have taken calculus, you may recall that one of the first steps we take in learning how to integrate is to talk about Riemann sums, where we approximate the area underneath a curve by just adding up the areas of a bunch of rectangles. That's essentially what we're going to do when we do a numerical integral. So the integral technique here is just to add up, the numerical integration technique is just to add up the areas of each of those rectangles. The area of each rectangle is going to be equal to the width of the rectangle times the height of the rectangle, which is basically just the value of the function at that value of x. So here's the code for that, and I'll let you kind of parse through the code on your own, but you can see a lot of the same structures that we've already dealt with. I have an initial value, I have a final value, initial x and a final x value. I'm going to divide the range up into some number of rectangles. I'm going to calculate the width of each one of those rectangles as being the maximum x value minus the minimum x value, and then divided by the number of rectangles. So I'm taking that range and chunking it up into a bunch of rectangles. Then I have this variable that's basically just going to be a sum variable. It's the thing where I'm going to store, I'm going to keep adding the areas of each one of those rectangles to this thing. I then do an integral by just incrementing the value of x from the initial x value up to the final x value by delta x each time through the integral. What am I adding to the total area? I'm adding exactly this thing that I showed you above. So the term in this sum is equal to the value of the function times the width of the rectangle, and I'm just adding that onto the total area. When we do this numerical integral, we get a value of 21.279999, and the exact value of this integral is 21 1/3. If I wanted to make this numerical integral more accurate, I would increase the number of rectangles, and I can do that on the fly now. If I do 100 rectangles instead of 20 rectangles, you can see, oh, we're getting a lot closer here. So now I'm getting 21.33. If I turn this up to 10,000 rectangles, now the rectangles are going to be super skinny and they should better approximate the shape of the function. The integral takes a little bit longer. You couldn't see it take a little bit longer, but we're getting closer and closer to the actual analytical value. So like I said, integrating that function is something that you have rules for doing. We don't really need a $1,500 MacBook Pro in order to do that. There are, however, functions that we use all the time in the quantitative sciences that are very difficult to integrate. Here's one of them. This is what we call a Gaussian. It's nasty. Unfortunately, it's nasty, but it is an incredibly common function in statistical modeling. It shows up all over the place in the quantitative sciences. We often have to integrate this thing, and we would do so using the same syntax that we had above. So here's a graph of a Gaussian. You may know it as a bell curve or a normal distribution. That's fine. It goes by many names. If I wanted to integrate this thing numerically, I would basically use the same dang code that we had in the previous cell. I'm just using a different function. Instead of that polynomial function, I'm using the Gaussian function that we defined, and I'd have some different integral parameters here. So we will come back to this idea of numerical integration later on. This is more of just an application at this point. I wanted to show this to you. We'll come back to it. But for right now, let's maybe hammer out one of these warm-up problems. So I want to do this prime checker. Let's write a function p of n that checks whether a number is prime. So def p, and it's going to take in an input variable that we'll call it n. So the way that I'm going to code this up is let's keep a number in mind. Let's say 29. I forget whether 29 is prime. The way that I would check whether 29 is prime is I would basically check whether 29 is divisible by all of the numbers that are less than 29. If 29 is going to be prime, then it can have no divisors, and we only have to check the numbers that are less than 29. So let's start with something dumb. Let's do for I in range. I'll start at 2, because we don't have to check 1, 2 up to 29. And we'll do if n% I is equal to 0, print n not divisible by I. All right, great. I think that this is going to work. So let's define that function, and I'll just go down here and let's put in 29. So let's see if this runs. Okay, so it ran, and I did. Oops, I see what I did. So I checked whether it was divisible by this, and I didn't want that. So I want actually not equal to 0. If n divided by I leaves some remainder, then that n is not divisible by I. So we'll redefine that function. We'll do 29. So check this out. 29 is not divisible by 2. It's not divisible by 3, all the way up to 28. All right, so really I want to find out. This isn't quite what I want to know. I want to find out if the thing is divisible by any of these numbers. So maybe I could change this, and I will just change this slightly. I'll change this. So if n% I is equal to 0, meaning it is divisible by the number, I'll print out the number that is divisible by. I'll say n is divisible by that number. So let's redefine this thing. And then I will rerun this function call. Okay, so we get no numbers that this thing is divisible by. Now, that's basically checking what we want to check, all right? But we need this function to give some output that actually tells us whether the thing is prime or not. So what I'm going to do is I'm going to create a new variable up here, just call it isPrime, and I'm going to set it equal to true. Or how do I want to do this? Let me set it to true. And if whoops, it should be true like that, lowercase. All right. So if I find an I that divides this value of n, basically what I want to do is I want to reset the value of isPrime. We're going to set it equal to false, because if I find a number that divides n, it will be false that n is prime. And then what I want to happen is I want this function to return isPrime. Okay. So what the function is going to do, it's going to start by assuming that n is prime, true. It's going to check all of the numbers less than n. If the number divides 29, or sorry, divides, yeah, well, let's do it like this for a minute. I just found another problem. We'll fix it in a moment. if the number I divides the input number, which we're calling 29 for right now, it's going to set is prime to false because we found a divisor, and then it's going to print out that the number is divisible by the thing. At the end of the day, after this for loop is over, the function is going to return the value of is prime. So the one issue that I ran into that I have here is that 29 is hard-coded into this program, and we actually want it to be n. So now I give this function some input value, and it's going to check all of the numbers less than that input value. This is actually pretty inefficient. If you can figure out why this is an inefficient way to do prime factorization or check whether a number is prime, post it in the comments or just yell at me on Slack. I bet you can figure it out. This is not we can save a lot of time in checking prime numbers, but this is fine for right now. So I'll execute this cell to run, to define that function. And it turns out that 29 is prime. So let's do 290. Great. So this thing seems to be working. All right, I'll leave it there. Hopefully this video is a little bit shorter than the previous one. I'll be dumping another one pretty soon. Talk to you all soon. If you have questions, let me know. Thank you.